คนเรียนเหลือแค่นี้แหละนั่งเลยได้ไม่เกิดได้ถึงผมว่าอาจารย์มาสอนผมนี่เที่ยงมาไปสอนตรงระเบียงดีกว่าเที่ยงมาเล่นบ้าเลยสัตว์ชิวเลยตอนแรกดีเข้าเลยไหนงอนเราไม่เข้าไหนงอนปวดวันเดียวมันออกเลือดมันเป็นบาดโซ่เลยว่าตัววะกินเลยนะนี่มึงเป็ดเหรอวะส่งมาไม่ส่งอะไรไหนส่งมาไม่ส่งไอ้นี่ไม่เป็นเหรอเขาเหรอโอ้ยเนี่ยมันไม่ยุ่งส่งอ่ะกูว่าเขามีเป็ดสีเขาเลยไก่ล่างไม่ส่งไม่เป็นไม่เหี้ยเลยยิงลงกี่ลูก3ลง15ไป15ลง3ไม่เท่าไหร่ไปตรงเลยเหี้ยเราบอกกูวิ่งก็สนามเลยมึงไปอ่ะตั้งแต่ต้องสอนไม่ดูเขาช่วยมึงไงเขาช่วยมึงไอ้เหี้ยไม่ว่าเขาช่วยมึง46นะเขาช่วย50เขาช่วยเยอะเกินไอ้เหี้ยไม่ดีอ่ะดีแต่แบบไม่ใช่ว่าปล่อยหรอกมึงรู้สึกผิดแล้วเลยไม่เขียนว่าตัดผิดแล้วเชื่อดิมันวันทูไปถึงโคตรเพื่อการศึกษาไปไอ้สัสการศึกษาทำสิ่งที่ educational purpose ไม่อาชีพเพื่อการสื่อสารไม่เราไม่ได้เรียนละมันคือเราเรียนทั้งคู่เลยใช่ไหมแม้มี2อย่างไม่ภาษาอังกฤษเพื่อการในข้าวมันเรียนไม่อังกฤษแบบอังกฤษเฉยๆอ่ะอยู่ในมีบนสุดอ่ะสุดท้ายเฉยๆอันสุดท้ายอะไรคือบนสุดอันสุดท้ายวะต่ำสุดคือ46 bro ไอ้เหี้ยอังกฤษเพื่อการสื่อสารอยู่ใน49เอโตฟักกิ้งเวย์ what คุณไม่ได้ทำมาผ่านเลยถามว่ามึงเคยสื่อสารไม่ได้ไม่รู้มึงแค่แบบเขาใช้โลอ่ะชิวแล้วพูดได้ว่านี่แหละไม่ได้ทำงานแย่เลยไม่ถึง9เลยมั้งไปชัวร์ไปคือคุณไม่เป็น2วิชาเรนดอมทำเลยประสบการณ์ใช่เต็มหรือไม่เต็มดีเอาเลยนะเลือกฟักไอ้เหี้ยเบสดูไอ้ดีไทยดีไทยไอ้ยังไม่เจออะไรเลยเจอได้ไหม39แล้วจะทำเที่ยงอยู่สัตว์การโอ้พี่ทำได้ไหมไม่เจออะไรเลยเอาไว้เครื่องบินเฮลิคอปเตอร์โอ้พี่ทำได้ไหมถ้าโอ้พี่อยู่โอ้พี่ทำได้ไหมเที่ยเราบอลก็แบบไม่มีทางเกิดแต่เราบอลเป็นซ้ายโอ้พี่โดน1ไอ้เหี้ยโอ้พี่ดูรองเท้าเราบอลดูไหมไม่เกี่ยวรองเท้าเราบอลดูไม่เกี่ยวโอ้พี่นั่นโคตรเท่เลยรองเท้าเราบอลโคตรโหดไม่เกี่ยวหนักชิบหายรองเท้าแม่งไม่เกี่ยวรองเท้าหนักชิบหายไม่เกี่ยวนี่มันพูดมาเลยบอยเก่าใช่ไหมเดอะบอยที่ภาษาไทยที่เราออกรู้จักเดอะบอยด้วยหรอบาโค้ดเลยสัตว์เอาบาโค้ดสังเกตว่ามอนยังว่ามีข้าวได้โอ้ยมาถือกันเหลวเรียนอ่ะน้องไอ้เลยสัตว์ไอ้น้องเรียนอ่ะหมายถึงแบบมาเรียนอ่ะSCI33206 จากที่นี่ก่อนลูกก้าเท่าไหร่ลูกก้าเท่าไหร่ลูกก้าแพงเจอแล้วเท่าไหร่ลูกก้ายิงเท่าไหร่เฮ้ยทำได้ไหมได้ทำระบบทำได้ไหม
ยังไม่เจอจริงขายเท่าไหร่ไม่มีตัวโตเลยครับก็ต้องเจอได้ดีกว่าขายเสียข้างหูเหี้ยเบื่อเอาแล้ววันนี้อ่ะแม่เรากลับบ้านพ่อมาขายไปอยู่แบบภาพแบบหายไอ้ใครเคาะอีกอ่ะโอ้ยไอ้เหี้ยทำไมโอ้ยเป็นคนประตูชนไม่กลับกลับครับเดี๋ยวมีชื่อมาเช็คชื่อครับเน็ตวันเวลคัมยูทูบครับเวลคัมยูทูบได้มาดู5 today is the on 6 of January 2024คนแรกครับนาวุฒิครับแล้วก็พยากรครับพยากรกินแบบไม่รู้นะครับผมว่าเริ่มจากวิบูลแล้วคิดว่าเขาไม่ใช่ครับคล้ายกันบ้างครับเดี๋ยวพวก605ครับเข้ามาที่ห้องก่อนนะ605เช็คชื่อก่อนครับพยากรณ์นะพยากรณ์
เฮ้ยใครเรียกอันนี้เขาเนี่ย
แล้วก็พันวิทย์ของไทยไทยนาพันวิทย์มาปะไทยพันเอาด้วยโอเค
เนี่ยเดี๋ยวชื่อเพื่อน
เนี่ยมีคนที่ว่าขอศิลปภพใช่ป่ะพันวิทย์อยู่ไหนเลยเนี่ยอ๋ออยู่นี่แล้วก็นัทวัฒน์ครับธนากรแล้วก็พักเลยเอาประตูเปิดแล้วเฮ้ยอย่าล็อกได้เลยล็อกเลยป่วยนะศิลปภพคือว่าศิลปภพมีอาการท้องเสียอานิวัฒน์ครับอานิวัฒน์สหรัฐสมัครในคิวแบบภูมาไม่ตีกองแล้วเหรอเขาก็ส่งมาฮะชวดโอ้ยเวลาโคนชวดคนประเทศเลยสมัยนั้นสวยงามแดนฟ้าแดนฟ้าเดี๋ยวปิดประตูนิดนึงครับแอร์ให้เย็นครับแล้วเรียกกูต้องการreal life ครับผมพยากรณ์เทนนิส
ยืมได้ไม่ได้เกินเราเรียน2 คนชุด
ภูมินันท์
เรียนหาบริษัทแสงครับ
นักเอกเอาหายป่วยแล้วหายสิเป็นเคสามเป็นเคไปไหนแล้วเป็นเคเอาเป็นเคยังไม่มานะครับแอปเซนไปนะ
4-2ก็ชนะ
นัทนนท์เห็นอยู่เป็นไหมโอเคครับสรุปงานคุณแข่งเองกันแต่ในงานศิลปกรรม
เฮ้ยไม่ได้หมุนเลยไม่ได้หมุนเลย
อ๋อแต่คุณไม่ได้แข่งแบบแกะสลักอะไรอย่างนี้ใช่คุณแข่งเอาเพื่องานเขาชื่อศิลปะเลย
ต้องการที่จะแบบยุค
อ๋อเอาไงเลยคนแข่ง
ก้อยซื้อ
คนแข่งว่าไงคนแข่งทำอะไรถ่ายรายการ
เป็นงานใหญ่ก้อย
ทำอะไรอ๋อเหรอครับผมคิดว่าคุณไปจัดดอกไม้แข่งกับโยน
ไม่ประทับใจ
ทักษิณครับทักษิณ
ให้กูเป็น
ทักษิณ
มันให้
ทันเกรด
ทักษิณ
เฮ้ย
ขากิน
แม่ฟังเลยสิริ
ป่วยเลย
ปานทำปานทำโอเคครับ
ก็รอ
เขารอเก่งชื่ออยู่นะปานทำจริงๆแล้วธนาธรนาริศไปแล้วเล่นเกมอยู่เลยเพราะว่ากาซิเดสครับผมเรียบร้อยครับ
จะเล่นทีมดี
พัทดล
FM
ขอเช็คชื่อพัทดล
มาอย่างแน่นอน
ภูเมฆภูเมฆเป็นกองให้เขาตีนะครับตอนนี้วิบูลย์ครับสวัสดีครับวิบูลย์อ้าวตอนเที่ยงยังเจอผมอยู่เลยวิบูลย์ไปไหนล่ะจอมเปิดรั้วโรงเรียนเลยคนนี้เปิดรั้วโรงเรียนไปไหนล่ะวิบูลย์ไม่เจอผมเกลียดน้ำเต็มอ่ะแม้ว่าจะเจอตอนเที่ยงก็ตามเป็นผู้ช่วยรปภในการเปิดรั้วโรงเรียนเพื่อกลับบ้านครับ
ซื้อที่ไหนกันพอเราต้องมีรูปไหนที่ไหนกันเอาเลยสิพอเราไม่เกี่ยวแค่สองใบเดี๋ยวว่าต่อไม่ต่อถูกไหมอ๋อถามก็ถามดาวก็บอกนะไม่ได้ไปกินเลยไว้ดูคนกรณีเดียวกันไว้ไว้ห้องไม่ได้ไม่ได้ใช้ขนาดต่อไปไหนก็รู้หมดเลยนะรู้เดี๋ยว
เอาจริงเคตายแล้ว
เลยเกมมา
ว่าผมแก้ยอดนะ
นี้เลยครับคือไม่ทำงานถึงบอกให้ทำงานมาเพราะว่าในพวกไปกับมันไม่เลยแม่มันโทษกูว่าทุกวันพวกกูอีกก็อยากจบโทรหาแม่ก็รู้ว่าคนอยู่ไม่จะบอกแม่แล้วเนี่ยแม่อะไรคือมาห้ามไม่ห้ามไม่ห้ามจบจะสามประตูมาใหม่แต่ละ4-3พี่แล้ว4-2จบไป3
เอาปกติรุ่นพี่คุณจะต้องเขียนรางวัลนะว่าอะไรนะปัดฉิมพิเศษวันอะไรนะจากเจ้าแต่คุณไม่เขียนแล้วรุ่นคุณจำได้อัตโนมัติหรือว่าแจ้งกันในไลน์ทุกวันนะ
มันลงกันในสตอรี่อ่ะ
ลงในสตอรี่อยู่แล้วปกติรุ่นพี่คุณผมเข้ามาตอนแรกเขาจะต้องเขียนนับวันถอยหลังนะบนกระดานปีนี้ไม่เจอ
วันจากเก้า
ไอ้ยัยสิวันนี้กูก็เศร้าที่ถ่าย
โอเค
แล้วก็
that's for
ก่อนมึงจะใช้ท่านี้หาที่เองนะ
your employer
แต่ต้องมาเพื่อแบบแค่เข้ามาคือมันควรจะควรจะ
วันละ3หรือวันละแบบเก็บที่เลยนะกาวมากดีเยอะเลยเนี่ยอันนี้มีเลเวลแบบ2,500นะกูซื้อเลเวล2,500กันแหวนของแหวนตัวอย่างตัดเลย
เฮ้ยนี่อ่ะ
Okay, we alive at the decision, which is actually it is a kind of reproduction. The nuclear fission talks mainly about the decomposition of the uranium-235, and that is an intermediate state, which is uranium-236. Now let's talk about the figure that describes equation A7. The input is neutron and uranium-235, which is the active isotope of the uranium. Here you have uranium-235 nucleus, and someone has accelerated the neutron, and neutron is moving to directly to the nucleus of uranium-235. Now neutron is absorbed into the nucleus of the uranium-235. It becomes uranium-236 with star. Okay, star is in excited state. And the nucleus before, because it's quite large, and when you increase the number of particles inside the nucleus become unstable, and those particles try to separate from each other, and it has the shape like this, and eventually it's going to be decomposed into nucleus X and nucleus Y. And in addition, we have also the output as few neutrons, okay, several neutrons. These are the neutrons that are different from the initial neutron. Okay, this is the outcome. And if you have furthermore uranium-235 in this area, okay, it might happen that this neutron will hit the next uranium-235 nucleus, and this process can occur again, can happen again. Okay, the reason why they don't write down the specific element for the daughter nuclei, such as X and Y. Okay, they simply use the unknown variable X and Y, like in equation 87. The reason behind that is the following: because it can be decomposed into several pairs. Okay, this is the number of nucleons. Okay, because let's forget about the sharp particle. The most important is the number of particles inside that, number of nucleons inside those nuclei. It can happen that sometimes the daughter nuclei can be very small or can be very large, like this. Okay, but typically, once they observe it and keep the data record, okay, the physics found that most of them would take place around for the lower nucleus. It takes place around 90 and 100 nucleus with 90 or 100 nucleons, and the bigger nucleus would be around 133 and 143. Okay, right. But in this region, we can still see the possible nucleus that can take place. Okay. One of the possible pair from figure 22 is the following. You have neutron and you have the fuel, which is uranium-235, and a pair that would be barium 141, which is an isotope of barium. And another smaller nucleus is krypton, right? And KR, what is that? Because I did work in this topic quite often. KR, element. Yeah, krypton. Okay, krypton is the smaller nucleus, and you end up with 3 neutrons. Okay, the krypton, the name is just are fission fragments, and most reactors in operation today also use the uranium as the fuel. Natural uranium contains, if you go to the mineral industry, the results suggest that most uranium has around 0.7 uranium-235, which is the active version, and the remaining 99.3 is uranium-238 isotope, which is a more stable version. Okay, the most, I think, the most stable version isotope. Uranium-238 can also absorb the neutron, leading to uranium-239, even bigger. Okay, it's even bigger, but not with high number of it to sustain a chain reaction by itself. So the chain reaction could take place from equation 87 or 88 because one of the outcome is the neutron, and it would initialize the next nuclear fission process. Okay. It tends to absorb the neutron, producing something different, which is the bigger nuclei, such as, for example, neptunium or plutonium. Okay, that's the way for uranium-238. Let's have a look at the chain reaction if you cannot completely see what it means.
9 เซนไม่อัพเดตมันอยู่นี่
หายไปไหนแล้วคุณไปไหนมา
ไปสักที่ไหนไม่ได้
อยู่ที่ห้องอะไรเหรอ ห้องที่พักอะไรเงี้ยเดินเลย
อัพเซนได้ไงผมจากนี้ไม่ได้นะ
พักกันตั้งแต่เที่ยงแล้วนะได้โอเคครับผมติ๊กให้ครับคุณก็ไปเลยอ่ะเดี๋ยวปิดประตูด้วยนะครับ เดี๋ยวแอร์ออกนะ Okay, you start the nuclear fission process by lighting the neutron, okay, to move to uranium-235, and sample is barium-141 and krypton-92. And of course, this would produce also further neutrons, and these neutrons will hit the next uranium-235 and just three neutrons, for example, in this process. According to this equation, you get 3 neutrons, right? These 3 neutrons will hit the uranium-235 nuclei in the process. And it can be decomposed into different pairs, for example, strontium and xenon. Okay, xenon. Inner gas is stable, and Y and I think iodium and Y. What is that? What is the name of this element Y? Y element. I think deuterium or something like that. Yeah, yttrium. Okay, yttrium. Okay, yttrium and iodium. And another possibility is niobium and antimony. Right, this one. English word okay, instead of Latin word. Yeah, those pair would be exactly the same as urea-purified. For example, you have 138 and 95, you get 141, right? You have 3 neutrons. 138
โคตรน่ากลัวที่โฮลี่ไม่วะ
and
ไม่
also we have 138,
เสียงไม่น่ากลัว
35. Okay, the number of neutrons from different process would further initialize the next reaction for uranium-235 if you have enough uranium-235 in that area. Okay, that was taken from the book number 1. If you have looked at another book number 2, this is the first generation neutron. You get uranium-235, you get the daughter nuclei such as barium-139 and krypton-94. And the neutron in the second generation will initialize the fission process again to uranium-235, uranium-235. You get xenon and strontium, for example, in the lower decomposition. In the upper decay, you may get cesium and I think RB, what is that? Rubium. Yeah, rubium. Okay, you may get rubium as the outcome as well. And in this second generation, you may have the third generation for the neutrons. And if the uranium-235 into different pairs, okay, and so on. Okay, you may get cesium. Rubium, okay, you may get cesium, rubium, and barium, krypton, rubium, cesium, the pair for each other, and xenon and strontium. And then you get the fourth generation even more, okay. But you know, this process becomes exponentially increasing. So the way to control the whole process is that you need to have a method to slow down the velocity or the speed of the neutron in each generation. Otherwise, it's going to need more and more uranium-235 and that could destroy because the energy will be too much for the system that can be controlled, it can control. Okay, and the failure could occur in the nuclear power plant due to the lack of good control for each neutron generation. Okay, the probability of neutron absorption by the nucleus is much greater for lower energy neutrons than for the higher energy neutron. For example, the energy less than 1 electron volt, okay, could initialize the next the composition of uranium-235. But if your neutron has too much kinetic energy, okay, too much speed, okay, it will not be absorbed in the next uranium-235 because the speed is too high and it can simply penetrate the nucleus of uranium-235. Okay, for uranium-235, the slow neutron are far more likely to cause friction than the fast neutron. Okay, due to the lower kinetic energy. You know, in dynamic system, the kinetic energy is the most important feature. neutrons can be slowed down by the collision with nuclei in the ceramic material, and this cooling material is known as moderator. Okay? Moderator can be made of graphite, carbon, which is quite simple, but it's in the solid form. Okay? It's not easy to use. But another possible way is the heavy water, which is the info. Okay? They use the letter D in order to differentiate from the deuterium from the hydrogen. Okay? They use hydrogen to use the D. Okay? Which is deuterium. The second isotope of the hydrogen. Now we have the figure of the reactor core. Okay. In reality, human has set up the system like this. Okay, this is radiation shield. If you go to most nuclear power plants, they're gonna be built like this. Okay. You have the radiation shield made of thick concrete. You may have field elements. You may have moderator material. As I said before, the moderator is the guy who tries to slow down the neutron movement. Okay, because if the neutron has too much kinetic energy, the next fission will not happen. Okay, we need to slow down the neutron, but not keep it still. Okay, we need to have the neutron with certain speed. Okay, and another way to control the fission process is to use controller. Okay, this will separate the nuclear fission from this area to another area. Okay, in order to protect the neutron moving to the next fuel elements. Okay, otherwise the fission could grow up exponentially, and that could be out of control for the electrical engineer or the guy who governs the whole nuclear power plant. Okay. In figure 25, this is the explanation. The reactor core contains the control logs, fuel elements containing enriched food. Okay, you have to. I don't know. Maybe you have to order the uranium from a country like Australia or something like that, or some countries in Africa. Yeah, I don't know whether we can find uranium to be found in Thailand or not. I don't think so. We need to import from those countries like Australia. Okay. Apart from famous beef for the steak in Australia, okay, we need to import uranium-235 as well if we decide to build up the nuclear power plant. Okay. Actually, nuclear power plant can be considered as the green energy, actually, because the waste from this kind of power plant is too little. Okay, comparing to the typical coal power plant. Okay, that could cause several waste in terms of air quality and pollution. But this one we in a good control, okay, in a good monitoring. This could cause very little waste. And the way to keep waste from this kind of factory is that, like in Germany, you have to build up the hole or the cavity under the ground, like 200 or 300 meters under the ground, and you will let the outcome of the fission process to stay there, okay, for a certain period of time. Okay, it's gonna be disappear. Okay. Also by the radiation shield, which is this one. Okay, and the rate of reaction is controlled by inserting or withdrawing the control of the beam. If you feel that the energy or the temperature in this area is too high because of increasing energy, you just put the control down, okay, so that you keep you separate the neutron movement from the next fuel element, and that's the simple way. Okay, if you want to increase more energy, like in the early hour during the daytime, okay, when some people, when the inhabitants get back home, they like to use more electricity. You have to or lift the controller up, and the process will take place more and more, and we can get more energy to support the requirement or the needs of the household or habitat in the early hour. Okay, the controllers are often made of cadmium, okay, which is very, very stable. It doesn't have any interaction with neutron or other nucleus after the fission process. Okay, cadmium is the guy who stay in neutral state. Okay, and one of the things that cadmium can absorb the neutron without making any additional reaction. Okay, so we should say thank you to the guy who discovered that cadmium is quite not neutral to everything in this process. In the nuclear power plant, the fission energy appears as kinetic energy, okay, heat, because there is Brownian motion of several molecules or kinetic energy of the fission fragment. Okay. And the way human adopts this energy to use in the daily life is figure 26. The control of a nuclear reactor is in a closed space, which is called reactor pressure vessel. Okay. And you just use a pump, okay, to put the water to be in the steam generator, and inside this you have a closed vessel or pipe for the water, the hot water that absorbs the energy from the nuclear reactor would go to the pipe. Okay, due to the heat or kinetic energy, the water will go by itself. Okay, and it's going to move in the solenoid or the coil like this. The reason is that we need to exchange the heat or the energy to the pure water in this area. Once the water in this area absorbs the heat, it's going to be boiled down to be vapor, or in terms of specific term, it's going to be called steam. Steam with temperature around 5 megavolt that would go here, and it's going to take the pressure, okay, try to push the rotor on the turbine, okay, and the turbine is connected to the shaft. The shaft is connected further to the generator. So once the generator that has the rotor, okay, inside the rotor we have several coils, and once the coils move and it just passes the magnetic field, it's going to generate electricity according to the Faraday's law, okay, that we have studied in the last semester. Okay, and the cooler water will go down, okay, because it's cooler, stay together, and when it's behavior is going to go down, and we can cool this water further by using another closed loop of the water, okay, if you need. Okay, but if the heat stops so much, it just be like this. And in order to let the water flow in the circular way in this area, we need to use the pump, okay, to force the water from the lower, from this cooling capsule to next to the heat exchanger capsule. Okay, if you take a look here, you can see that this is the first circuit of the water, and here is the second circuit of the water, and here you may have the third loop of the water. Okay, so water is the guy who absorb the energy and transfer to different locations, and we use the energy from electric power. Okay. It might be quite complicated, but yeah, it's useful for us, and you don't need to pay attention to that, okay? Except for being a guy who works with these nuclear power plants. Okay, fission reactions are always exerted. It means the energy at the kinetic energy and the input is always greater than the kinetic energy in the output. Okay. You have more energy at the input, and you have less energy for the output. The fission fragments have greater binding energy on than the original nucleus. Okay, of course, the remaining nuclei should have high binding energy. The nucleus that has higher binding energy, the more the stable nucleus is. Total kinetic energy of the fission fragment is enormous, about 200 mega electron volt, okay, which is a different level compared to the energy of the electron transition in different shells. Typically, the amount of the energy released by the fission of a single heavy radioactive atom is about 100 million times the energy released in the combustion of one molecule of the octane used in the gasoline engine. So, yeah. In one day, if human can build up the system of nuclear fission, okay, this would be very efficient and just carry the fuel very little. Okay, let you just carry all the little amount of fuel like uranium to refine, but you can have the energy like 100 million more than the current combustion engine. Now let's talk about the energy calculation. If the disintegration energy Q per event is 208 mega electron volt. Calculate the total energy released by uranium-235 of 1 kilogram. Okay, first thing first, you need to compute the number of nuclei per kilogram. Okay, these will be found from the atomic number. No. The number of nucleons, okay, which is 235, and Na, which is Avogadro number 6.022 10 to 23, and 0.235. That's the amount of mass for 1 mole. Okay. This is the number of nuclei per 1 mole, and here is the amount of mass of uranium-235 per 1 mole is only 0.35 kilogram per mole. Okay, and after you make the division, you're gonna get the number of nuclei per kilogram, which is quite large here. And the energy would be number of nucleon times the heat, which is integration energy, which is to the 8 convolts per nuclei. And after that, you're going to get the energy per kilogram, okay, which is the product of these two numbers, the result of the equation 89. And you get 5.33 as 0.1 10 to 26 mechanical per kilogram. And the second question, how many kilograms of 235 uranium 235 uranium-235 would be needed to satisfy the world's annual energy consumption, which is around 4 times 10 to 22. Okay. So we're gonna need to compute the amount of uranium-235 mass. Okay, just take the division. Number of the mass of uranium-235 would be the required energy 4 times 10 to 20 divided by the amount of energy per kilogram. Okay, then you can determine the number of kilograms. Well, you're gonna get 4.6845 1026 kilogram, and that's around 4,000 tons per year. Okay. That's the energy for the whole world. If each fission provides 2 megaelectron volts, how much uranium has to undergo fission per unit time to provide 300 megawatts of thermal power. So let's talk about a nuclear power plant that generates the energy in terms of electricity around 3,000 megawatts, which is actually 3 gigawatts, right? And they would like to know how much uranium we have to burn in the nuclear fission process. Okay, by using the result in equation 89, this one, the number of nuclei per kilogram, the amount of uranium-235 isotope required to 3 times 10 to 9 joule per second can be computed by this equation. 3 times 10 to 9, which is the energy we need per for these requirements. Okay. What is joule per second? So we can convert this 3 gigajoule per second. As I said, it's 3 gigawatt, which is equivalent to 3 gigajoule per second. And the number of uranium per kilogram is the result we have calculated earlier, which is this one, 2.5626. And yeah. Oh no, the energy per kilogram, right? Which is this one. Once you divide it, okay, this is the way to convert megaelectron volt to joule. Okay, you just multiply it with somehow like the electron shaft, and you're gonna get the amount of uranium in kilogram, like 4. Oh, sorry. You divide it with the number of nuclei and the heat that you're gonna need per nuclei, and then you can use the calculator to compute all these. Then one of the things is that we need to convert the energy from megaelectron volt to joule, okay, because the requirement of the energy is in joule. And after that, you get 3.65 times 10 to the 5 kilogram per second, which is not easy to understand because it's far from the typical number. We may need to convert it to appropriate unit, which is milligram. Okay, it means would burn the uranium-235 only 36 milligram per second. Now let's move to the next type of nuclear process, which is nuclear fusion, okay, which attracts a lot of attention nowadays. In a nuclear fission reaction, 2 or more small light nuclei combine to form a larger nucleus. Okay, and nuclear fusion is something different. Okay, you start from light nuclei, small nuclei, and you try to build it up as nucleus, big nucleus. But we could get also the least things. 2 or more small light nuclei are combined for a larger nucleus. When 2 or more light nuclei combine to form a heavier nucleus, the process is called nuclear fusion. Fusion means something that we try to melt it down, and those can be combined together. Okay, usually the mass of the final nucleus is less than the sum of the mass of each original nuclei. there is a loss of mass accompanied by a release of energy. Of course, one of the most observable example takes place on the sun, right? Which use with hydrogen. 3 examples of energy liberating fusion reaction are in the following sequence. The first one is something about protons, okay, or hydrogen. 2 protons are the nucleus of the hydrogen combined to form deuterium, okay, which is denoted by H21 or D21. Another result is positron, okay, positron would be the result. And another one is electron neutrino, which is denoted by nu, okay, nu zero zero. First we have the nucleus of hydrogen and another nucleus of hydrogen. Okay, they're going to combine to be deuterium to 1. Okay, but if we have one more proton, the proton re-emergent as positron together with electron neutrino. Yeah, in physics, it's quite important to evaluate the energy of each process, each decay. Q can be found from the mass difference between the input and the output. In this process, the input would have more mass, and that's why we're going to get energy from the outcome, okay, according to the unbacked Einstein formula, then E equal to mc squared, but c squared is converted in real form, which is 931.5. Okay, and when you substitute the mass of each particle, okay, we have 2 nuclei. We have 2 nuclei of hydrogen. It's going to be subtracted by the mass of deuterium and the mass of positron. Okay, but yeah, it's simply the same as the mass of electron. And finally, after the difference, we're going to get 931.5. And because this is the energy per atomic mass unit, okay, the difference can be found in atomic mass units. And after this multiplication, you get the energy, which is 0.9315 megaelectron volt. The positron will annihilate with an electron in the cell for 2 gamma rays. Okay. According to this process. Okay. Once this process takes place, you get hydrogen, and you have hydrogen to nuclei of hydrogen. And there is an electron in that area. First you get deuterium nucleus and positron together with the electron. The electron and positron will combine together each other, and we're going to get the gamma ray, okay, which is a kind of energy in terms of photon. And in this process, if we have to look at the energy calculation again, okay, we have one more mass of the electron at the input, okay, and we make the subtraction, okay, multiplied with 931.5, we get the energy in the scale of 1.9543, okay, greater than equation 94. And after that, the hydrogen in that area could be combined further to the resulting deuterium, okay, deuterium here. And we're going to get a bigger nucleus, which is helium-32, not helium-42, which is the alpha ray. Um, and we have also gamma, okay, which is anti-photon. And that's why you can see that we can have the photon of the light from the sun due to this process. And let's try to compute the energy from this process: mass of hydrogen, mass of deuterium, subtracted by mass of helium-32, K1.007, and 2.01. That's the mass of deuterium subtracted by the mass of helium-32. We get the energy of 5, okay, which is even greater than the energy in the first, in the second, the first one. Okay, 5 is greater than 1.9, that's 2 times twice. The third process can be either 3.1 or 3.2. The hydrogen is further, okay, we have more hydrogen. The hydrogen is further combined with helium-32, we get helium-42, which is now the stable, one of the most stable nucleus in nature, okay, helium-42. And we get also proton. If you compute the energy from this process, you're going to get the mass difference here, the input and the output, 19 megaelectron volt, okay, which is much greater than the energy in the second process. Okay. In another version, in the second possibility, because we have more and more helium-32, right? Helium-32 can be combined to each other. It's going to be formed as helium-42 and 2 nuclei of hydrogen. Okay, and hydrogen will stay in that area, and it will act as the fuel for other process, like in the first process. Now let's have a look at the energy in this equation. Mass of helium-32 twice, and mass of helium-42, the alpha particle, and mass of proton or hydrogen. So once you multiply with 1.5, you're going to get the energy around 12.859, okay, which is comparable to the first one, to the first possibility. The first possibility would generate more energy, but this one is also quite comparable. The above 3 sequential process is known as proton-proton cycle because you start with only hydrogen, okay? It's going to be transformed into bigger nuclei. The above 3 sequence process is known as proton-proton cycle, and the physicists believe that this is the state of the energy liberation in the sun and other stars, which is rich or full of hydrogen. Okay. And that can cause generate energy to other stars in the solar system or in the universe. Okay, those 3 processes can be illustrated in these figures. You have hydrogen in you get the neutrino, electron neutrino in the photon, and you get deuterium together with hydrogen can form the hydrogen helium-32 together with the gamma ray, nucleus electron, and neutrino, and proton. Proton. Helium-32, yeah, that's the way on another side in the same setting. Okay, hydrogen and hydrogen becomes hydrogen and deuterium, and further you get helium-32. helium-32 and helium-32 combined to be hydrogen and helium-42 in another hydrogen. And this will be very stable. Okay? So we don't need to worry about helium. As from the reactions, the liberated energy is carried partly by gamma ray, photon, and neutrino. Okay. So it means the sun always generates the neutrino all the time, and it can reach us here on Earth, but it's hard for us to detect because the neutrino is very small, it's neutral, okay. It doesn't have any interaction with the magnetic field, so we cannot detect easily. Gamma ray are soon absorbed by the dense gas, it rises its temperature. So the proton combine with electron to produce again gamma ray, which in turn are also absorbed by the gas within a few centimeters. Because it moves with the speed, it can capture the electron immediately, only by few centimeters. While almost never interact with matter, neutrino escape from the star. Okay, it doesn't have any interaction with neutrons. Carrying about only 2% of the whole energy that process. These energy liberated fusion reactions are called thermonuclear fusion reactions. Okay, the net energy released, which can be calculated from the mass balance, turns out to be 26.7. If you combine all of these, it's going to be around 26.7 megawatt. If the sun were to continue to radiate at its present rate, which is about 130 million watt-hour, it would take about 75 billion years. เท่าไหร่อ่ะ75,000 ล้านปีนะถ้าที่จะดำนะครับเห็นไหม75,000 ล้านปีเราอายุรุ่นเราแค่หลักร้อยนะ I don't know what is going on if the sun doesn't shine anymore to exhaust its supply of protons. The fundamental challenge of nuclear fusion is to give the nuclear enough kinetic energy, okay, so that it can combine with each other. To work on the repulsive Coulomb force between them at close proximity. Okay, because the nuclei of hydrogen, okay, are positive. They are going to repel each other, and you need to put the energy, sufficient kinetic energy to the nuclei. For two nuclei, to fuse, they must come together to within the range. Okay, the range of the nuclear force, typically on the order of 2 femtometers. So the nuclei should be also very close to each other, around 2 times 10 to 15 meters. That's the unit of electrophilic. It's called femtometer. At the distance of 2 femtometers, the potential energy of 2 protons is on the order of 1.1 10 to -30 joule or 0.7 magnitude. So you have to overcome it. The temperature for a gas with the average vibrational kinetic energy is 3.5 kV times T, and which is equal to 1.1 10 to 30 joules. So if you convert this energy to the temperature, it's going to be equal to 5 times 10 to 9, okay? 5,000 million cubic, so which is extremely high, the temperature in the fusion process. Now human tries to artificially make this process on Earth, and the major problem is that they have to find the metal that can sustain or be good enough to protect the whole system from this at this temperature 5,000 million Kelvin. Okay. Kb is the Boltzmann constant. Okay, that's what we have seen before in the chapter of heated gas, right? The temperature must be on the order of millions Kelvin. So the nuclei are to have enough energy to support the electrical deposit and achieve fusion. So you have to create the environment with several millions of Kelvin. Okay, so with that high energy, the hydrogen nucleus will have enough energy to be fused with another nuclei. Fusion reaction that appear most obviously involve the deuterium with hydrogen to one and tritium, 3-1. On Earth, human tries to build up this process. Okay, deuterium to 1, hydrogen to 1, and together with another component, another copy of this deuterium, you're gonna get helium-32 together with the neutron. Okay, and if this is possible, we can determine the energy from this process. Okay. Mass of deuterium twice, and then mass of helium-32, which is the uncommon isotope of helium. Okay, you substitute by mass of helium-32 and substitute by mass of neutron. Oh, this is wrong. This is failure. It's not positive. Okay, it should be negative. Because here you can see it's negative. Okay, after you convert the mass difference to the energy, you're going to get the energy around 3.267, but that's still to be okay, because this is on the order of mega electron volt. And another one is deuterium. Now we get tritium, okay, which is the unstable isotope of hydrogen and the common hydrogen. Okay, like this. In this process, if you compute the energy from the EFC squared, you get the energy around 4 mega electron volt, which is a little bit higher than the first process, deuterium becoming helium-32, okay, which is like 32. Instead of helium, okay, we can also hydrogen from with single proton. 4 mega electron volt. And another possibility is that the deuterium and tritium could be formed up as helium-42. Okay, and after you compute the mass difference, you multiply with the magic number 931 to the C squared. You get 17 mega electron volt. Okay, this one is even greater, okay, than the former energy. The reason why we get more energy because we are dealing with big nuclei. Okay? When you are doing something with big nuclei, you will gain more energy. Okay, now we arrive at the first example. about the nuclear fusion. Okay. Yeah, when you deal with bigger and bigger nuclei, what you gain will be also higher energy. Okay. We have had this process, and it's the combination between light nuclei or small nuclei, for example, helium-32 and deuterium. Okay. So the first and the second element only hydrogen and helium. We did talk about lithium.
It's not cheating.
Okay, the outcome will be helium-42 together with hydrogen. Okay, to start from something strange like helium-32 and deuterium. What you get is when you get the typical nuclei such as helium-42 and hydrogen-11. Okay, or protein. Now we are going to compute the energy from this process. We start with helium-32 and deuterium and helium-42 and hydrogen, right? We substitute all this value into the mass difference and multiply with magic number 931.5. You get 80 megaelectron volt, which is even greater than this amount. Deuterium and tritium, but this one is helium and deuterium. Something greater than 18.352. Okay, all particles in nature are now. We move to the next topic, which is particle physics. Okay, almost at the end of this subject. Almost at the end of this chapter. It's something about particle physics. Okay, now we finish everything about nuclear process. All particles in nature are subject to 4 fundamental forces. So before we go to the particles, the first one is a strong force. Next one is electromagnetic force. Third one is weak force and gravitational force. That's what we experience every day. The strong force is responsible for the tight binding of quarks to form the neutrons and the protons, and the nuclear force that binds neutrons and protons to nuclei. These forces represent the glue, okay, that holds the nucleons together, and is the strongest force of all fundamental forces. This is the strongest one. It's a very short range force, and it's negligible for separation greater than 1 femtometer. If your particles are quite apart from each other, greater than 1 femtometer, 1 femtometer is equal to 10 to negative 15 meters. Okay, that's the strong force. Now we are arrived at the electromagnetic force. We are using this kind of force. Okay, human has applied this kind of force in most daily life. Okay, but it's not the strongest one. If you are able to apply or use the strongest one. It's going to be very energy efficient. Anyway, the second one is electrowave. For to use it in electric motor or any other application about magnet, which is about 10 to 2 times the strength of the strong force. Weaker around 100 times. It's 100 times weaker than the force, the strong force in the nuclear level, nucleus level. It's responsible for the binding of atoms and molecules because you have nucleus which is positive, including proton, right? It's positive, and you have electrons that move around the nucleus. So that kind of thing is the electromagnetic force, electric force, and magnetic force. Okay, and this also happens in the molecules. It's a long-range force, okay, that decreases in strength as the inverse square, according to the inverse square of the separation between the interact particles. The weak force is a short-range nuclear force. Okay. It's exhibited in instability of certain nuclei. It's involved in the mechanism of beta decay. Its strength is uncomparable. It's 1 million weaker than the strong force. Okay. Electromagnetic force is even more useful or more considerable. The gravitational force is a long range, and now we move to the last one. Gravitational force is a long range. Okay. You can still get the force from other stars even they are very far from our current location. Its strength is very, very weak, okay, but it's still observable. 10 to maybe 43, okay, of the strongest force, or you can say it's million, 10 million times weaker, okay, than the strongest force. So, but there is still negligible force from this kind of thing. This interaction might take place due to planets, stars, and galaxies. Its effect on elementary particles is negligible because it's very weak. The gravitational force is by far the weakest of all the fundamental forces. Yeah. At the moment, we know only 4 forces. Maybe in the future, you may discover something more. More than fiction. I often describe the forces between particles in terms of the action of field particles or quanta. Forces between particles are conveyed by an exchange of the field quanta. Okay, this is the way that physics is invented in order to better explain what is going on when particles transfer the force to each other. Okay, they use the term quanta. Okay, it's like money. Yeah. It's like you pay the money to something and then you have influence on someone. Okay, this process is analogous to the covalent bond between 2 atoms by an exchange of sharing electrons. Now we're going to summarize all these 4 types of force into a single table. We have few aspects about those 4 forces. Well, we start from the weakest one, gravitational force, weak force, electroweak force, and strong force. Relative strength is around 10 to -43. until 10 to the 38 of the strong force. Okay. Of the strong force. And electromagnetic is around 100 meter than the strong force. The weak force is in between gravitational force and electromagnetic force, around 10 to the 13 to 10 to 6 weaker. Okay. Strong force. The range, we believe that the gravitational force has infinite range, okay, infinity. So it acts in every distance, okay. And the strength of the gravitational force decreases with the radius of the distance squared. In electromagnetic force, same thing. Its observable range is infinite, and the strength decreases with the distance squared, okay, between one particle to another particle. In the weak force is in the range less than 10 to the 18. Okay, it's even smaller if you put something very close to each other. So there's the range in meters. It's going to be weak force. But if you let the particle stay in the Fermi or femtometer less than 10 to 13, you would observe the strong force. Whether it's which kind of direction, which kind of force direction is going to happen. Repulsive or attractive force. Gravitational force is attractive force. Electromagnetic force can be either attractive force or repulsive force. It depends on whether you have the same charge or the same pole of the magnet. Okay. They're both weak. Force could be also in terms of repulsive force and attractive force. The same holds for strong force. And this is the key thing, the tricky thing in particle physics. Physicists believe or invent the idea about carrier particles. Okay, it's like to pay money to someone, you're gonna have attractive force to someone. Okay. Particles would have graviton, okay, to transfer the energy, and electromagnetic force they just use the photon to carry the energy. And in weak force they use W plus boson, W minus boson, and Z0 boson. And in strong force they have gluon, okay, which is what you have seen inside the nucleus of proton and neutron. Okay. Now we look at the first type of the fundamental particle, and that's quark. Okay. But the time is over right now. I'm going to keep my stuff here and try to move to the next room, M604. Okay, if you have any questions, just let me know. If not, then see you next week, right? Bye bye ครับ สวัสดีครับ
ขอบคุณครับขอบคุณครับแม่งยังหนาวอยู่เลยเยี่ยมปิดแอร์เลยนะกูปิดแอร์เลยนะแม่งเย็นเลยโอ้ยทำไมมัน
เป็นเพราะอากาศข้างนอกมันเย็นมากกว่านี้ใช่ป่ะเย็นนะเย็นข้างนอกก็เย็นนะใช่โอ้ไม่ขีด SK ท่าน้ำโอ้
ระวังโทษไปไหนแร็กเกอร์นี่ถ่ายไว้หมดเลยห้องอยู่ไหนวะเนี่ยประตู2อ่ะโอเคเจอโอ้โหไอ้เหี้ยอันนี้ไม่เย็นเจี๊ยบเลยวะเออโรดิเชอร์ อะไรวะไปดูวางไว้ตรงนี้กัน
ไม่